Our analysis and our examples so far have looked at only single degree of freedom systems that resulted in either a first order system or a second order system. Now we're going to look at what happens when we have multi-degrees of freedom, which are going to result in typically fourth order or higher systems. So the first thing that we're going to see that is going to be different is that instead of one natural frequency in our system, if it's second order, we're going to have multiple natural frequencies. And this happens again if we have 2 degrees of freedom or more. A fourth order system will have multiple natural frequencies in our system. And we'll be able to find these natural frequencies really the same way we can for second order systems, but in transfer function form we're going to find that the denominator is fourth order, fourth degree or higher. And if we find the roots of the denominator, which is to say the poles of the transfer function, we're going to be able to use those to find our natural frequencies. And it still holds true that the poles in the transfer function form are the same as the eigenvalues when we're in state space form. So finding the eigenvalues or the poles, we're going to be able to determine what our natural frequencies are. One thing we're going to see is different when we make our Bode diagrams is that the peaks are not going to be necessarily located at natural frequencies or near natural frequencies. There's not really going to be a resonant frequency the same way there is in a second order system. So we can't make all of the same analogies we made for second order. Second order has a lot of special things we can do that's a lot easier to make an analytic approach to it that we can't do for these multi-degree of freedom systems. We're also going to see that the different outputs or the different observables we have in our multi-degree of freedom systems are probably going to behave differently from each other. When we look at the Bode diagram, they're going to behave differently at different frequencies. So they might have peaks, they might not be at the same location, and they might not be near either or any of the natural frequencies in that system. When we're doing the modeling step, we might find that it's easier to actually start in state space and then convert to a transfer function form, although we could do everything in transfer function form. But using Bode, doing some of the analysis, having that transfer function is often going to be easier to work with. And again, I want to caution that once we go above second order systems, not all of the analysis is going to transfer over to how we do it for higher order systems, but some of it will. So through the example, I'll try to be pointing out where can we use the same ideas and where is it going to differ from second order systems. Let's take a look at this 2 degree of freedom system. It looks very similar to one we looked at back when we were doing state space modeling the first time. So we're not going to go through all of those same steps. We're not going to go through the free body diagram and all that. In our modeling step, really what we're going to focus on is the analysis step here of when we have this input of 2000 sine 5t, how are the two positions going to respond, the z and the y? So we're going to be looking for the stability of the system, which we're going to be able to assess by the poles of its transfer function or the eigenvalues in its state space form. Finding the natural frequencies, we're also going to get those from the poles and the eigenvalues if it is indeed an underdamped system. And now we're going to be able to look at its response when u is the sinusoid. How's the position of mass 1 and mass 2 going to behave at steady state? And we're going to be able to do that again through a Bode diagram. So first step is we need a mathematical model of our system. So to do that, I'm going to start this in state space form because we've already done this one previously. So I'm going to define my states from vertically down, z dot, y, and y dot. I'm not going to show the equations of motion here. Again, you can refer back to the state space model we made for this system previously. We have a single input in the system, u, that's acting on m1. It's going to be important to note through the analysis here that we have a 2 degree of freedom system. However, there's only a single input and it's acting just on m1. If this system were to have an input on m1 and m2, the analysis we are going to do from here is not going to hold up. So the fact that it was one sinusoidal input, we can use a Bode diagram in a very similar way we did it when we were looking at 1 degree of freedom systems before. So if we make our equations of motion, if we replace all of those variables with the state variables, we're going to get our x dot equation. So we have our 4x4 A matrix and our 4x1 B matrix, since we have one input and we have 4 state variables. So again, it looks exactly the same as the one we did before. The one before, though, I think the input was on M2 versus M1, so the B matrix is just a little bit different. And then if we make our Y equation, where we have our C matrix and our D matrix, now we have our A, B, C, and D matrices fully developed. And we have them labeled here. So C is 2x4. We have 2 observables, the position of M1 and M2, notably Z and Y, or X1 and X3. Our C matrix and the D matrix is just going to be a 0 vector. All right, so the modeling step is done, at least using a state space approach. Now what we can do is move on to the analysis, really more of the spirit of this unit. All right, so what can we do with the state space model? Well, really I'm going to use it and go into the transfer function form, because that's going to be easier to work with when looking at the next step, our analysis. So recalling back when we first looked at state space and we saw that we can go between state space form and transfer function form. And analytically, we can do it using those ABCD matrices. Or we can use the SS2TF function in MATLAB, which I'll look at later. But going back one step, right now we have everything algebraically. So for the moment, I'm going to stick algebraically with our M's, our M1, M2, our K's, and our B's to get analytically or algebraically the transfer function form. And I'm not going to do this by hand, but we'll look at Mathematica and do this operation and see what our transfer functions should be. Going into the Mathematica notebook, I've put in the matrices, the A, B, C, and D matrices, just as we developed them for our state space model. And now in Mathematica, I'm going to do that exact operation here that's going to let me take these 4 matrices and convert them. Since we have 2 observables, we're actually going to get two transfer functions. And it's going to come out here in this form where we're going to have a vector of 2 elements. So running this, we see that we get these 2 transfer functions out. The top one is going to be in the same order as our C matrix. So the C matrix here, the first row is pulling out Z, and the second row is going to be pulling out the Y value. So the first transfer function we developed is Z over U, the input, and the second one is Y over U. So it's in not the greatest form yet. We see we have S's, S squareds, S cubes, and S to the 4th. So we will have a 4th order system, and that's going to come when we have 2 masses in our mechanical system. So I'm just going to clean this up a little bit using that collect feature. So we see here, they do share the exact same denominator, and that's going to happen when we have only 1 input in the system. And then I'm going to do the numerator for the Z term, and then the numerator for the Y term, just so they come out in the way that we're going to like them, where we're collecting on the S's. Keep in mind that we will write them in descending powers of S rather than ascending powers of S. So this notebook file is available, but I'm just going to take these, this denominator and these 2 numerators, and I'm going to make the transfer functions from them. So getting that output from Mathematica, cleaning it up a little bit, putting it in our desired order, we see here that we have, I'm going to call it G sub Z for our Z transfer function and G sub Y for our Y transfer function. So again, same denominator, we're 4th order, but they do have different numerators. So we have our transfer functions algebraically, which if we can do something algebraically, that's usually good to do. But now I'm actually going to apply the values that we were given for the M's, the B's, and the K's so that we can actually find numerically what our natural frequencies are and kind of proceed from there. So if I put in the given values, notice that the S to the 4th term on the denominator has a coefficient of 1 here. This is actually coming out of MATLAB, which I'll show in a second. But all that happened was that MATLAB automatically divided every term by that M1, M2, which was originally the coefficient of S to the 4th, so that the leading coefficient was 1. Now again, these are 4th order transfer functions. The previous analysis was for 2nd order systems, where we're finding the damping ratio, the 1 natural frequency. This is 4th order. It will give us 2 natural frequencies, and we can't come up with a damping ratio really in the same way we did for a 2nd order system. So now that we have our numerical values for these 2 transfer functions, we can jump into MATLAB and start doing some more of our analysis. So in MATLAB, I'm going to retrace some of the steps that we just went through. So I have my values for k, for b, for m that were given. In MATLAB, I'm going to repeat some of this by making the matrix A. So I'll start there. All right, so we have our A matrix. I have it in now numerically. I'm not going to do this symbolically like before in Mathematica. But what we can look at is now that we have a numeric A matrix, we can find its eigenvalues using the eigen function. All right, so if we do that and I look at lambda, we see here we have 4 eigenvalues. We always have as many eigenvalues as the size of our square matrix. And if we look at the first 2, they are complex conjugates of each other, and the second 2 are complex conjugates of each other. And also, if we look at all 4 of them, their real part is negative. So what this is telling us is that all of the eigenvalues, remember these are also the poles, as we'll see in a second, of our transfer function, they're all in the left half plane. Therefore, we can answer that first question, is our system stable? Yes, all poles / all eigenvalues are in the left half plane of the system. Now we can also look at what are our natural frequencies. Again, we can do this from the state space using these eigenvalues that we just came up with. So if we just showed them, I can find the natural frequencies by taking the magnitude of all of the eigenvalues. Now, the magnitude of the first 2 are going to be the same. The magnitude of the second 2 are going to be the same because they're complex conjugates. So when I get out, I'm only going to use the first and the third term we see in line 181 here. I can use the second and the fourth. It wouldn't make a difference. But if I do that, I'll just rerun up to that point. We get our 2 natural frequencies of this 4th order system, this 2 degree of freedom system, is going to be 2.09 radians per second and 0.957 radians per second. We're not going to find like a damping ratio in this one. It's not going to have the same meaning like it had for our 2nd order system, but we can at least investigate how do these natural frequencies affect the behavior of the system when we are giving it a sinusoidal input. Now I can go about making the other matrices, the B, the C, the D, again from the slides, and then I'll use here the SS2TF function, and we're going to get the exact same results as if we started in Mathematica and then applied all of the numerical values. All right, so remember SSTF is going to give us 2 outputs, a B value, and we see here these are again the 2 numerators of our transfer functions. The first one is for Z, the second one is for Y, and then one denominator that they're both going to share. So what I can do is, again, looking at A, the denominator, these are the coefficients in front of the s to the 4th, 3rd, 2nd, 1st, and the constant term. So right away I can look at the poles, or really the roots of the denominator, which is the poles of the transfer function, and I can see what they are equal to. So if I find the roots of A, those are the poles of my transfer function. And let me show the poles first. Those are the poles. If you go back, those are the exact same values we got for the eigenvalues of A. And if I display their absolute value or their magnitude, again, we get those same values. These are the 2 natural frequencies of this system, 2.09 and 0.957 radians per second. Now I can make those transfer functions using the first row of B and the second row of B. And this is what on the other slide I was calling GZ and GY. So TFZ, again, looks exactly the same as what we had on the slide, and TFY looks the same as the slide as well. So in MATLAB, I now have my 2 transfer functions built, and they're in transfer function form. Now what I'm going to do is a little bit different than before. When I make my Bode diagram, when we come down to 199, 200, I'm going to make a Bode diagram of the Z transfer function and the Y transfer function, and I'll put them on the same plot. And then I'll make, obviously, a legend for them. So this is what we get, the Bode plot for both transfer functions at once. So just visually, initially, what we see is that they do both have a peak near 1 radian per second. And if we see where that peak is, they're slightly offset from each other, but we see that the peak is about equal to 0.97 radians per second. And then on the other one, again, it's more or less the same. If we go here, if we look, that is pretty close to that lower natural frequency of 0.957. So that kind of lines up with what we saw before for second order systems. However, if we see where this other peak is, well, the y doesn't really have a second peak, and the blue, the z, kind of does. So let's just see where that is about. The peak is around 2.28 radians per second. It's actually higher than our larger natural frequency there. So again, we can't interpret where the peak is going to be like we can for the second order system, where it's at that resonant frequency, which is often, for low damping systems, close to the natural frequency. But we can calculate ahead of time. Here, it's in a different place, and it's going to be not as easily predictable, and we're not going to get into the math behind it in this course. And we can see similarly, they both have an inflection point in the phase diagram around the same point here where that first natural frequency is, but then they kind of diverge in what they're doing out further. And actually the peak of the z, we see there, it's 2 radians per second. That's, again, kind of close to the second natural frequency, but we don't see anything like that happening for the y diagram. That's only happening in the z. All right. The way we need to actually use the Bode diagram, though, we have to look at how is the system going to behave based on what the input frequency is. And when we go back to the prompt, we see our input frequency, as a reminder, is at 5 radians per second. So that's where we want to investigate our Bode diagram, is at 5 radians per second. So coming back to it, we want to see what happens at 5 on both of these for the z and the y. Right, so we see that for the z, we have a magnitude of negative 47.3 decibels. I'll convert that in a moment. And for the y, it's lower, negative 67.5 decibels. And since we want to know what's happening at steady state, the full equation, I want to also look at what's happening to the phase. So again, 5 radians per second, 5 radians per second, negative 173 degrees, negative 297 degrees for the y. Now I'll do a quick conversion here. I want to convert it from the decibels to that linear magnitude. So for the z, we have 0.0043, and for the magnitude of y, we get this 4.2 times 10 to the negative fourth in linear terms. Now, summarizing it now on our slide, that's the mz we just calculated in linear terms, and we have the phase from the diagram, negative 173. I want to put that into radians. And for the y, again from the plot, the magnitude and the phase expressed in radians. At this point, we can find the steady state equation analytically based on the m and the y. Remember that m, the magnitude, is the ratio of the output to the input. So when we multiply each of these m's by the input amplitude, which is 2000, we can get here what the output amplitude is. So for the z, we have this 8.62 times sine of 5t, again that's the input frequency, minus 3.02, and for the y, 0.85 times 5t minus 5.19. When we have multiple degrees of freedom, but there's still only one input, like we have in this example, we can use the exact same idea we used for a second order system, that at steady state, all the outputs are going to be their output amplitude times sine or cosine, depending on what the input was, at the driving frequency, and then plus whatever the phase difference is. So we can find the position, steady state position for z and y, both of those drawing from the Bode diagram. Again, I'll caution, if we had multiple inputs on the system, especially if they were at different frequencies, this would not work. We can only do this for multi-degree of freedom systems when there is one input acting on the system. Now, it wouldn't matter if it were at M1 or M2, that would affect that B matrix, but it would not affect the analysis procedure that we're going through. So we know analytically what the steady state Z position should be and why. Now let's verify it using simulation. So I have a Simulink model of both of the transfer functions here. So this is right out of the MATLAB. I transcribed them into my GZ and GY. I have that same input that's going into both of them because this is Z over U and then this is Y over U. So this is my U. And if I just open it up and look at it, it's that input 2000 is my amplitude at 5 radians per second, just like given in the prompt. So that input is going into both transfer functions, and then I'm gathering their outputs. I'm using that concatenate. So again, the order that my data will come out will be U is the first one, and then Z is going to be my second column, and Y will be my third column. And that's all being saved into this sim out that we'll see once we run this. I'll point out here, because this is a little bit more complicated of a model, I am doing a little bit of customization in these settings here. This is probably usually closed. So if I open this, these are usually the defaults here. I made my max step size smaller than the normal is. I think the max is normally like 1 times 10 to the negative 3. So I made it smaller to get a little bit more precision. And the tolerance, I think I also toned down a little. But if you're getting kind of choppy results from the simulation, you might want to make these smaller. So you can do that in the settings. And finally, I'm going to run this for 200 seconds. We're going to see that the transient phase is actually pretty long here. So you might run it for a shorter amount of time, see that you're not at steady state, and then increase with what this number is. But we'll see in our results that 200 seconds will be long enough that we'll kind of just enter the steady state in this example. So briefly in the code, 213, I'm running my Simulink model. And then I'm getting my data out. We see we'll have this sim out like we've seen before. We'll have our timestamps, we'll have our input U, and we'll have our 2 outputs, the Z position and the Y position, and I'm going to plot them. I'm actually going to do this in 2 figures. I'm going to do it the full time series of the 200 seconds, and then I'm going to kind of make a zoomed in one once we reach the steady state. And now I'm just going to run it. Right, so this is the first figure that comes out. Again, this is the full time series from 0 to 200 seconds. And if we see what's going on in our input is steady always, because that's the 2000 sine 5t. So that's just for reference. We have what Z looks like and what the Y position looks like. So clearly in Z and Y, if we look at what's happening, we have these big slower oscillations that are eventually dying out. The same thing is happening in Y. So this is the transient phase that we are not trying to predict in this course. But we see that those transients die out, and by the time, at least when we're zoomed out here, by the time we get to about 160 seconds, to be a little conservative, we see that the Z and the Y now appear to be at steady state. And we'll check that when we zoom in. So the first, again, 160 seconds of this, we're in the transient phase, and then we appear to go into the steady state phase. That's what we were predicting using the Bode plot. So we can look at the zoomed in figure, and we see that here I chopped it off. I actually started at 190 seconds through 200. So it's just that tail end of the simulation. But now if we look at the Y and the Z, Y is actually still a little bit unsteady because the peaks are not uniformly the same across it, but it's going to be close enough for comparison. Probably we would run this even a little bit longer so that we ensure that Z and Y are at their steady state. But let's see where our peaks are. Looking at the peaks, my Y value for Z, I have a peak value of 8.63 with a little bit of rounding. And for the Y, I'm getting a peak value of 0.863, again, with a little bit of rounding there. If we go back briefly, those amplitudes do match, at least to pretty much 3 decimal places, what we predicted using the Bode plot. So the amplitude of Z is about 10 times that of Y, and that was confirmed by the plots we just made in simulation. So finally, for this multi-degree of freedom system, we were able to analytically calculate what the steady state behavior was going to be for our 2 masses, for the positions of our 2 masses. We did analytically using a Bode diagram. We could do that because we had only a single simple harmonic input into our system. If that were not the case, we cannot use this same technique that we've been using. And then we saw through simulation using a Simulink model and running our input through that we have verified that we get those same, at steady state, those same amplitudes.